Okay, so my name is Ethan Austin, and I work in the Barbo lab at Duke University this summer, working on muon energy detection with a muon hodoscope. And my mentors were Dr. Philip Barbo and two graduate students, Samuel Hedges and Longley. And so why this matters, a muon hodoscope allows for more accurate measurements of radiation and particles. You can further understand particle interactions, which can help us to improve the standard model of particle physics, which basically is just a set of rules that governs the way the world works on a particle level. And this could help our lab to calibrate detectors to improve the search for dark matter, and more research in this field could lead to new technological development. So how radiation detection works. So all muons are detected by standard radiation detection procedures, and all radiation detectors are comprised of a scintillating material and a photomultiplier tube. A scintillating material is just anything that releases a photon when hit with radiation, and so we use different types for this experiment. And a photomultiplier tube is this thing down here, and what that does is whenever a photon strikes the photocathode, it releases an electron, and then we use high voltage differences to amplify this signal because initial signals are very weak, and this allows us to look at the signals from each particle or photon of radiation. And so muons and the hodoscope. Muons are formed in cosmic ray interactions, so basically cosmic ray strikes particles in the upper atmosphere, and a muon is released. And they're a lepton, which is a subatomic particle related to an electron, but a muon has more mass and doesn't have a charge. And so they're fast moving and high energy, and because of this, and because they don't have a charge, they can't be shielded against, they don't fully deposit their energy in the detector, meaning they continue through, and their energy deposition is constant, or at least nearly constant, as they travel through a detector. And so their total energy cannot be determined through normal methods, so you use a muon hodoscope, which uses coincidence logic and a detector array. So as you can see, we have 12 detectors on top and one on the bottom, and the main purpose of the muon hodoscope is to determine when a muon passes through the detector, because since they can't be shielded and don't deposit energy fully, a muon will travel through one of the top 12 and then through the bottom one. And this allows us to determine when a muon has actually been seen. And you can also approximate the path of the muon by measuring the angles between the detectors, which can be used for energy calculations. And so the development of this, we began by planning out the detector, what we needed to do in order to make it possible to measure muon energies correctly, and then design parts for the detectors. So we had to design holders for all of the radiation detectors so they'd be in the right position, and we could maintain constant angles and constant ratios between the locations of each detector. And then we had to use the 3D printer machine shop to make parts for this and set up the detector assembly. So that's the thing in the bottom right. We hook up all the detectors in such a way that they can measure the energies we want to look at. And then this is a NIM logic system. So we pull the signal from every single one of these detectors, and they pass through a discriminator. And what the discriminator does is there's a set threshold for voltage output. And so if the output signal from any of these detectors is higher than that threshold, the discriminator will give off a square wave with an on signal, which can then be put through further logic gates. And so in order to determine when a muon passes through, you take an OR signal from all of the top detectors. So when any of the top detectors trigger, that wave is on. And then you put that through an AND signal with the bottom detector. So that means if any of the top 12 and the bottom signal trigger at the same time, it passes an on signal. And we use that on signal in order for our detection purposes. And for data collection, I used a signal digitizer, which is this thing right here that's covered up by wires. And what that does is it takes the voltage waveform from the output signals from radiation detectors and converts it to binary code to represent these values. And we use the AND signal from the NIM logic to trigger this. So we only record signals whenever a muon for sure passes through the detector. This makes the code easier, and it also makes data storage it makes data storage not a problem. And so after that, you use an interpreter file to convert the binary into a root file, which can then be used with the root programming language developed by CERN to analyze the radiation data. And so for data analysis, the coincidence logic nearly guarantees the muon is the actual signal, and with the calculations done, it comes out to about 1,000, like one in 1,000, maybe a random coincidence, but everything else is a muon. And with the root programming language, we can look at complex energy graphs for all of the data. And whenever we get the muon signals, we can use higher resolution detectors because the muon hodoscope itself is built with plastic scintillators, which have fast decay time to prevent random coincidences, but that also means their energy resolution is low. And so we tried BGO, which is bismuth germanate, and NaI, which is sodium iodide, as our middle detectors to get more accurate energy readings. So, first of all, the BGO data. Again, a BGO has a shorter decay time than sodium iodide. It's more efficient, but it has poor energy resolution and it's somewhat outdated. And there's a thin energy deposition path, so if you can see the detector right here, it's not very wide. And so that means the muon doesn't pass through very much detector and it gives off less energy. This also means that as the angle changes, it's less of a path increase, so it's harder to determine the difference between the different angles in the hodoscope. So this was the top channel frequency for that BGO run, and basically what this means is whenever we got a muon signal, which of the top channels did it come from? And with this run, we had a lot of problems, or not a lot of problems, but we had a lot of signals from detector 4, which meant something was wrong. Either the voltage threshold was different than the other detectors, or there was a light leak, but we addressed this before the next run. And then these are the BGO signals for the top triggers, and so it just goes 1, 2, 3, 4, 5, 6, 7, 8 through 12. And you can see that while a couple of these are pretty good, a lot of them are very poor, at least if they're supposed to match the Landau distribution, which is what this red curve is. And so we couldn't really use these energies to give us accurate calibrations because there's very large error and they don't provide precise energy measurements. So we decided to move on to sodium iodide, which has better resolution. And that's another indication of bad data. This is the angle versus the most probable value for the integral. And so as the angle increases, the path through the detector should also increase. And so it should deposit more energy, and the integral should be larger on average. So the most probable value should also go up. And most probable value is approximately like a mean of the integral distribution. It's a little different, but that's a good approximation. But as you can see, this is not positive linear. It's slightly negative, but pretty much straight, which means this isn't good data to analyze. So then sodium iodide was used instead. And it's less efficient, it has a longer decay time, but since we're not using it for the trigger, the decay time isn't a problem. But that means it has higher energy resolution and it's better for precise calculations. So this was the top channel frequency during this run, and you can see it's a lot more balanced. Channel 4 is still a little higher, but we fixed some issues, so everything came out a little better. And this was the signal for the plastic detectors on top. I included this basically to show why we have the other detector in the middle, because just using the plastic channels from the top array, you don't get precise data readings either. But when you use the sodium iodide signal, you can see that we get very nice data that we can use to calibrate. Now what happened in the last 6 detectors is accidentally the angles that we made were too large, and whenever a signal would pass through the top array and the bottom detector, they wouldn't actually go through the sodium iodide all the time. So you get a lot of random noise signals that just happen to pass through the sodium iodide detector at the same time. And this means that these signals can't be used for calibration, but if we had more time, we'd adjust that in the future run. But the top 6 provide very nice values for the integral distribution as the angle changes, and this can be used to calibrate our detectors. And so this was the raw plot for the linear calibration. And as you can see, for the first 6 points, we get the very nice positive linear function. But then as the quality dropped, it started to mess up. So basically the way we do energy calibration is we're trying to find the ratio between the integral value and the real energy value for the detector. And so first you have to find a value for how much energy is deposited by the muon per unit of path length in the detector. And for sodium iodide, that's 4.85 mega electron volts per centimeter. And then you basically just multiply that by the path length. which you can calculate using standard trigonometric functions. And so when we took the first 6 good points and fit a linear regression to the data, we got a pretty good fit. It looks slightly nonlinear, but we didn't have time for very long runs, so this provided pretty good information on what the calibration was. And so what we did after we found the calibration values, which is basically you take the slope and intercept of that linear regression line and you put the integral value into x, and the y output is what your energy is. And so this is a raw background that we took with the sodium iodide. So this is just every signal a sodium iodide detector gets over a 30-minute period. And as you can see, there's a lot of different peaks which represent different energy gamma rays down here. Usually they're thorium, uranium, things in concrete. But over here we have the muon peak. And it's kind of hard to see, but at these high energies we get that peak. And with just the integral values, it doesn't appear very well. But when we use our calibration that we determined from the linear regression, we get that for the muon peak. And while this still isn't great because it was a short run, it's a lot more precise and it's a better shape for determining exactly what the energy of the particles are. And so if someone else in our lab wanted to calibrate the detector for muon detection, they could put it inside the hodoscope and determine what they need to multiply all of the points by in order to get this nice muon peak. And the only problem with this is because sodium iodide detectors have nonlinear energy relationship at low energies, that the muon calibration kind of voids all the low energy data. As you can see over here, it kind of just falls apart. But it works very well for muons. And so the future outlooks for this project, the muon hodoscope, again, can be used by my lab to calibrate detectors, and potential use for SNS detectors, which is a big experiment out in Tennessee where they look for coherent neutrino scattering. And it can also be used to just remove muon noise from other experiments, so you can look at the coincidences and subtract out those points, so you're not looking at muons when you don't want to be. And you can also just measure muon energies if you need to do that for your experiment. And those are my works cited. And I'd like to thank all of the people that helped me in my lab, Dr. Barbeau, Sam Hedges, and Long Lee, the NCSSM groups that helped us with this project and funded us, and some of the sponsors from outside that helped to fund our program and the transportation. So are there any questions?